In this video, we are going to discuss about stress transformation. First, we need to understand what is stress at a point. Here, we consider a body that is subject to several applied loads, P sub 1, P sub 2, and so on. And inside the body, we assume a arbitrary point Q, which is experiencing the effect of all these forces. We could see the two force components, the delta Fx, the normal component, and the delta V sub x, which is a shear force component. Delta A would be the area of the point where delta A tends to 0. Next, we see the stress plane. Here we have three stress components, the sigma sub x, the tau sub xy, and tau sub xz. There are three stress components which are acting on the plane, whose normal will be in the x direction. And when we consider the stresses, for the subscript tau xy, the x would be the plane and the y would be the direction. The first subscript is the plane, and the second subscript would be the direction of the stress. In case of the sigma sub x, there are two x's, the sigma sub xx, but we simply denote it by sigma x. For a particular point, the arbitrary point we considered Q, the force is divided by the delta A, the area where the delta A can be made smaller and smaller. We could have three stress components, the normal stress sigma x, which is delta Fx divided by delta A, and then we have the two shear components tau xy and tau xz, which are determined as a ratio of delta V over delta A, where delta V is a shear force. We could do the same thing for the other cutting planes, the x plane, the y plane, and the z plane, and we could get the corresponding stress components. Now, what's stress transformation? Stress transformation is simply transferring the current stress in a given coordinate system to a different coordinate system. So it's basically changing the coordinate system. In this case, we are considering x, y, z coordinate system to x prime, y prime, and z prime coordinate system. And this process is what we call as stress transformation. To simplify the process, we ignore the three-dimensional stress. Rather, we stick to two-dimensional. We call it as a plane stress. So for the case of plane stress, we assume the z-directional stresses, which are the sigma sub z, tau z x, and tau z y, are equal to 0. Which means that we are only left with three stress components. One would be the sigma sub x, we have the sigma sub y, and the tau sub xy, which is equal to tau sub yx. They are equal. Let's consider a simple problem. Here we could see that a body is subject to stresses 115 megapascal and 245 megapascal in the two perpendicular directions, and we are asked to determine the normal and shear stress values at an E-plane which is inclined at 65 degrees. So what we do here, to be in equilibrium, we consider the force balance F sub n equal to 0 and F sub t equal to 0. And we could determine the normal stress and the shear stress across the plane which is inclined at 65 degree. The area terms get cancelled because they are equal on both the terms. So the dA component, the area component get cancelled, and that leaves us with the two stress components, the normal stress being 222 megapascal tension, and we have the shear stress which is negative 48 megapascal. Now coming back to stress transformation, what we have done in the previous example is we have the stress values for a given coordinate system, which is sigma sub x, sigma sub y, and tau sub xy, and we convert these numbers to a different coordinate system, which is nt plane. Since the xy plane is transformed to nt plane, and we have the new stress components which are sigma sub n, sigma sub t, and tau sub nt. You can see here the plane is oriented at an angle theta. The AA plane or the AA surface, so we transform the stress from XYZ plane to NTZ plane, and we assume the Z component stresses to be equal to 0. Here we can see the stress transformation equation, and once again we are considering only two-dimensional to make life easy. So we could determine the stress, the normal stress and the shear stress component in the plane which is inclined at angle theta.